Continuing 6-6. Click it here. 6-6. Continued. We talked about, at the beginning of this, what a vector was, how to move vectors around, how to plot a vector at the origin, go out to a certain point, vector notation, the component notation compared to the IJ notation, and how they're the exact same, where components is easier to work with once you know what the laws are. IJs are really good for proving things that are true about vectors, because then you could just use regular algebra laws. Alright, so today's lesson is how to apply vectors, so vector applications. No, this one works. So we're going to be talking about vector applications, some of them, and we'll get to more of them as we go through. So first vector application. It's called static systems. Black marker actually works. Maybe it'll work. Now a static system, let's go simplistically. If this is the floor, you're going to love my little pictures now, and you are standing on the floor, right? And you weigh 200 pounds. How would you represent that with a vector? The force of you standing on the floor. First of all, which way would the vector be pointing? Down. And its magnitude would be?
200.
200. So that's all we need to know about that vector. It's facing straight down, and it has a magnitude of 200 pounds. Okay. Now, if you have a vector of 200 pounds facing straight down, your body is going through the floor. So something else has to be happening. What else is happening as you're standing on the floor, besides your weight pushing down on it?
There's a force being pushed back up.
There's a force being pushed back up. Laws of physics. Gotta love them. So the floor is exerting a vector in the opposite direction. Well, this marker's dead. And it is also affected by... It is dead. Good job. 2 points. And it is also pushing up at the same 200 pounds. Now, if the floor was... it was this marker that did it. Won't use that one again. If the floor was rubber, right, and you stepped up onto it, you would push down with 200 pounds, but it would only push up with maybe 199, and you would actually sink into it a little bit. So when one of these forces is off just a little bit, you start moving in that direction. The only reason that you are not going through the floor and the floor is not pushing you up into outer space is the force down and the force up is exactly the same. So when you add them, oh, by the way, what sign does 200 pounds down get?
Negative.
Negative. So we consider this a negative 200 pounds, where this one down here is a positive 200 pounds, and the sum of them has to equal 0. So when we're talking about static systems, it is the sum of all the force vectors equal to 0. Sum of all the force vectors equal to 0. So when we talk about static system, sum of all force vectors equals 0. That's all there is to it. It's actually quite simple. All right. Ready? Now we can go crazy. Here's a building. Ground, windows, couple stories tall. Here's the door into the building. Great pictures. I love pictures. Artistic abilities. And this is a store, and they want to hang a sign out on a bar. So this is some kind of sign. Now, if they're going to hang it straight onto the bar, do you think that's going to work? Why?
It's gonna want to go like that.
It's going to collapse, right? So what do?
Make it a triangle.
Give it a little support. So it gives you a support bar here, coming down, attaching to the building. So that will hold the sign up. You can't, if you ever try to hold 10 pounds straight out for very long, your arm is going to feel horrible in about 10, 20 seconds. So if they have this sign, they want to give it a little support, and they have this bar going perpendicular and then at an angle. So I'll tell you what this angle is right here. Let's make it 60 degrees. Let's make it a 60-degree angle with the building. Okay. So what kind of triangle is that? 30, 60, 90. This is definitely a right angle. And what I want to describe is, at this point here, the cool thing about physics is if you take the weight of an object like that table and you kind of balance it on a pin, all the mass of the table goes to the head of the pin. So it's called what's called a point mass system. So all the weight of the sign goes right into that point, which is really kind of a weird way of thinking about it. We want that to be the origin on a piece of graph paper. So if we set this up as vectors on that point, that being exactly where the sign's weight is, what would be the first vector you could think of? Oh, I have to tell you something. The sign, let's let it weigh 500 pounds. Let the sign weigh 500 pounds. So just like you standing on the floor, it has a vector going straight down with a value of 500 pounds. So you start here and you go straight down with that vector. And this would be 500 pounds. Magnitude now, not anything else. Now that it's going straight down with a vector of 500, what would you consider it as a ij or a component vector? What would its components be? It's 500 straight down.
Degree.
Component vector value of that vector.
-500.
Part?
Yes.
Hmm?
Yeah.
Which one's which?
0, -500.
0, -500. So this vector is literally 0, -500. The direction is straight down, so the x value or the I value is 0, and it's going down with a value of 500. So its magnitude is 500. All right, what other vectors are working on this weight? Well, one of them is this vector here. If it goes along the pole. Now you have to think about this. The sign is trying to go down, and that support pole is going to push up, just like the floor over here. So we're more interested about the up. We already took care of the down. So when we talk about that vector going up, it's going to go up at that same slope. So it'll start here and it'll go up at an angle. What do I know about that?
60 degrees.
Here? On the other side. So what angle am I interested in? This one. And this is 30 degrees. Do I know the magnitude of that vector? How much weight that support beam is holding?
No.
No. So that becomes one of my unknowns. All right, there's one more vector.
90 degrees.
It's the 90-degree one. It'll be going along the x-axis. But you have to think of it. This thing's trying to pull down. This bar is trying to pull straight into the building. So the last vector is going to be this direction. It's a straight vector off in that direction. Do I know the magnitude of that vector? No. But I do know something. If I call this one V, call this one W, and we'll just let that one be 0, -500. It's actually easier just to leave it that way. Then what we can do is rewrite everything in terms of V, W, and that last vector. And the sum of these three vectors has to be 0 because the sign's not moving. It's staying right there. All right, so all I need is a vector for V, a vector for W, and a vector we already have. So what can I say about vector V? What do I know? Not much. other than the only component working on it is what?
The sine.
But it's only moving along the x-axis. So what's 0 in this case? Well, this one was 0, 500, negative 500, because it was going straight down. This one's going straight to the left, so what's its...
0.
Which one's 0, the x or the y part?
The y.
The y, because x is moving and y is not going up and down. So for one thing, I know that the second component is 0. What's the first component? What does it have to be eventually?
500.
500 was the force going down. This one's going to the left. The only way I can describe this 500 is two representations. It's 500 down, but it's also the magnitude of that vector. So what don't I know about this vector v?
The magnitude.
The magnitude. So why not just call it the magnitude of v? That's definitely what vector v is. It's the magnitude of v comma 0. Guaranteed without a doubt. That one's not too bad. W, on the other hand, we won't be able to do that too, because W's got an angle to it, and I don't know what its magnitude is, and I don't know what its direction. Well, I do know what its direction is. That gives me a little bit of help. But I can't do the same thing. I can't throw it right into a component. So what's another method of dealing with vectors? I showed it to you at the end of last class. Writing a magnitude and direction vector.
Cosine, sine.
The cosine sine thing. So what we're going to do here is go magnitude of W, component with the cosine of the angle and the sine of the angle. That's the formula? Right? All right, so I don't know what the magnitude of W is, so that's my unknown. But I know cosine and sine. I know what the angle is. The angle is 30 degrees. So W is going to become the magnitude of W. What's the cosine of 30 degrees? Do I need to draw my special triangles?
Square root of 3 over 2.
Square root of 3 over 2. What's the sine of 30?
1/2.
That's the 1/2 one. All right. So now I have all three of my vectors, v, w, and my third one. So if I take v, and I take w, and I take my third one, and I add them all together, the answer should be 0. Okay. So let's see here. We'll put that one last. V is magnitude of v comma 0 plus w, which is magnitude of w square root of 3 over 2, 1/2. And lastly, we need to add on 0, negative 500. And we want this to equal 0. I went off the screen. That's all right. Now, how do you add vectors? Oh, by the way, there's something wrong with this line. This is a vector plus a vector plus a vector equals
Something that's not a vector.
that's something that's not a vector. This is called a scalar. How do I make it a vector? Well, I could write it this way. With the brackets, what would be the two numbers?
0, 0.
0, 0. Or you can just write the little arrow on top. And that becomes the 0 vector, which is 0, 0. Or 0i, 0j. All right, so how do you add vectors together?
Yeah,
You add the first component, and then you add the
y.
second component. Don't think of them as x and y. I and j would be much better for vector language. So the first one is going to be magnitude of v, square root of 3 over 2, magnitude of w plus 0. That's not too bad. Magnitude of v plus square root of 3 over 2 times magnitude of w plus 0, which is that, comma. And then when you do the second component, you get 0 as your first one, so you don't have to worry about him. 1/2 of the magnitude of w plus, well, actually, minus 500. 500. And we want this to equal the 0 vector. So the trick here now is to find out what these magnitudes are equal to. So how would you do it?
So both equal to 0.
Set them both equal to 0. Because if this is the 0 vector, both of these components have to be 0. The easy one, of course, to solve is the second one, because that's just a straight linear equation. So if I solve this one, I get the magnitude of W is equal to what?
250.
250. And positive at that. So that represents 250 pounds. What am I supposed to see you over here?
Yeah, I forgot. I'm sorry.
That's why I have a calendar and I had it on there and everything. Now remember, W is the support beam. So this support beam is holding 250 pounds of the sign. Okay. To solve for V, I just go back to this equation and do a little, substitution. So when I put in W, I'm going to get magnitude of V plus square root of 3 over 2 times magnitude of W, which is now 250. Oh, and we want this to, darn it, equal, that's ugly, 0. So what's the magnitude of V? Well, this, negative. Because all you have to do is move it to the other side. So you get the magnitude of V is equal to negative square root of 3 times 250, which is the same thing as negative 125 square root of 3. What's that equal to in real numbers? Well, approximate numbers.
Negative 216.
Negative 216.5 pounds. So the perpendicular bar has to hold a lot more weight. Well, no, a lot less weight. The horizontal line is holding the 250 pounds. Kind of cool. So if you design your bar that's the 60 degrees off the building, you have to make sure it holds 250 pounds. Has to be able to hold that all by itself. The bar coming off the building has to at least hold 216.5 pounds. And then you get into people that actually design these things. Of course, they go above and beyond these numbers just in case the wind blows and starts shaking your sign, or other forces get introduced into it. But that's all there is to static systems. Yay! That's good with that.
Is that 216?
That's what she said, yeah.
Yeah.
216.5. Now, you can get into more complex static systems that have two off angles, like a rope tied on two poles and you're dangling someplace in between them, and how much force is required on both of the ropes to hold you alive. I have a problem that has Indiana Jones crossing a gorge, and you have to find out how much weight is on both parts of the rope.
On the test.
Extra credit. I can send that to you in your email too. Indiana, well, I call it Indiana, not Indiana Jones, Illinois Jones. I think I call it. All right, last topic. Dot product. So 6-7. Not to get confused with scalar multiplication or scalar product. Much different than dot product. Scalar product is 3 times a vector -2, 5 is equal to the vector -10, 15. It makes it 3 times as long in the same direction. That's a scalar product. Dot product, you're going to do a calculation based on 2 vectors. You're going to do a calculation on 2 vectors. So whereas scalar product is a number times a vector giving you a vector, a dot product is going to be a vector dotted, don't call that times. I know times is usually dot, but you really want to say v dot w. When you do a v dot w, you're going to end up with just a number, a scalar. So a v dot w does not give you a vector, but scalar multiplication keeps it as a vector. Does that kind of keep those two straight and you'll be fine? The way we define it is if vector v is ab, and we dot that with vector w, which is cd, then the answer is going to be ac plus bd.
My question is, I don't know if I'm supposed to know this.
Okay.
Why is that negative 10?
I just made it up. Oh! I don't know. What is it supposed to be?
Negative 9.
Yeah.
That's why I was like, I didn't know.
I was thinking of the
something
2 and the
was
5.
-9.
3
I
times.
meant negative 6. Oh, now I can't multiply.
Wow, we're all messing up on that one. Negative 6. But you're the only one that caught it, so 1 point on the test for you.
No.
Be like, Harry Potter and all those points they give away and take away. I should do that. That'd be awesome. You don't answer questions in class? Lose points. Answer too many questions in class? Lose points. I'm joking.
Honestly.
So, vector dotted with a vector, you just multiply the first two components, add it to the product of the second two components, you're done. Very simplistic, right?
Yeah, right.
Oh, it is. So if you have vectors like -2, 5, dotted with 4, 3, then all that happens is you get -2 times 4 plus 5 times 3 for a grand total of 7. So the dot product of these vectors gives you a scalar called 7.
So what if you put like I's and J's in there?
If you wanted an IJ notation, you like that one better? You do the same thing.
Oh, okay.
You just ignore the I and J and you look at the coefficients.
Oh,
That's why I like components better,
okay.
because I've seen people do this. If you do like 3i plus 4j, and you dot that with 2i plus 7j, up j, dyslexia kicks in. I've seen people foil.
Oh, that's what I was just doing just now. Oh, okay.
That's why I'm saying it's so much nicer if you just look at the components. Because then you're just going product of those two plus the product of those two.
So what about the I's? They don't like...
You ignore them completely. It becomes 3 times 2 plus 4 times 7.
And then you just add them
Yeah.
all at the end?
And it has nothing to do with the I's and the J's.
Oh, okay.
It has nothing to do with the I's and the J's. Properties. Just like if you learn how to add, subtract, multiply, and divide, there's properties that go with them. With real numbers, you get associative, commutative, distributive, identity, inverse, all that fun stuff. So the dot products have a few properties. One, v dot w is the same thing as w dot v. Basically, you can call that the commutative property of dot products. Commutative property. Two, if you have u dot v plus w, now when you look at these notation, it's kind of falls back under that sine of an angle is equal to a ratio, and sine inverse of a ratio equals an angle. You have to understand what the pieces mean. What's sitting out front? What is this thing called?
U.
Yeah, but what's it called? Is it a scalar or is it a vector?
Like,
It's a vector. If I take two vectors and I add them together, what do I get? A vector. And if I take a vector and I dot it with a vector, what do I get?
Scalar.
A scalar. So when you start recognizing what you're supposed to be getting, and you start not getting that thing, then you did something wrong. It's like taking the sine inverse of something and getting a ratio. It makes absolutely no sense if you think about it. So when I set this equal, I got to be really careful of what I write. So this is going to turn into u dot v plus u dot w. Does it make sense?
Yes.
Well, this answer over here is supposed to be a scalar. When I dot product u and v, I get a scalar.
Oh. Which is
When I dot product things together, I get a scalar, which is just a number, but we call it a scalar for purposes. And over here, I get u dot w, which is also a scalar. And two scalars added together is just another scalar. Property of real numbers type thing. All right. What's this equal to? 0 or 0 vector?
Vector. No, 0.
Pick one, please.
0.
What do you think?
0 vector.
0? Or 0 vector?
0. Well, is it like the inverse where the vector?
I'm asking you a question. What is the 0 vector dotted with a vector?
0.
0, because the dot product always comes back as a
0.
scalar. And scalars are not vectors, they're just numbers.
Oh.
Favorite true-false question of the century. True or false? And people will put false all the time. Not
Is
gonna
it
lie.
true or false question on that?
Oh, I'd love to. I think I should. If you do v dot v, dot a vector with itself, what do you think happens? Think about it. If you have AB dotted with AB, what comes out of it?
A squared plus B squared.
A squared plus B squared,
Oh,
which
A
sounds
squared.
really familiar to something else.
No.
No, before, well, vector language.
I don't know.
Magnitude. It's really close to the magnitude. What's it missing? The square root thing. So this is equal to the magnitude of v, but it's missing the square root thing, so squared. So a vector dotted with itself is its magnitude squared. Okay. Then we throw in something like this. If you have CU, what's C? Scalar or vector?
Scalar.
Scalar. What's U?
Vector.
Vector. CU is?
Scalar vector.
No, it's either a scalar or it's a vector.
Scalar.
It's a vector.
Vector.
Because a scalar times a vector gives you back a vector that is C times as long. C times as long. If we dot that with V, what do you think I can do with the parentheses?
It can go what?
Can I shift them?
Yes.
And just do U dot V and then multiply the answer by C? Sounds reasonable, doesn't it? U dot V and then multiply that answer by C. Now, C is a
Scalar.
scalar. Okay. So a scalar times a vector is a vector. A vector dotted with a vector is a scalar. Here we have a vector dotted with a vector first, which is a
Scalar.
times another scalar gives you back a.
Scalar.
So it seems reasonable that that works. If I went through the process and something went a little weird, then something is definitely wrong. Great. Should I prove it? Let's prove the last one. Proof. And we could do it componently. Let's let U equal AB and V equal CD. So this would be C times the vector AB dotted with the vector CD. So far, so good. So what's C times AB? CACB, if you want to write it that way. I'll leave it in that order. CACB. I'm alphabetical by nature. And then over, oh, I shouldn't have used C. Let's call that, I have C in two places. Let's call that phi. Phi is just a scalar. So phi A and, I forget if it's phi or phi. I think it's phi. I like phi because I can go phi, phi. And over here CD. So what's the answer to that?
Phi AC.
Phi AC or phi AC or whatever the heck is pronounced.
Plus
Plus
BD.
CBD. Okay. Now, one way of proving it is to rip it apart differently, but I think it would be easier just to go to the other side and show it comes out to be exactly the same. So the other side, question mark. You have to do u dot v first here, so you go c times ab dotted with cd. And if you dot the ab and the cd, oh, this is phi. You're going to get phi times ac plus bd, right?
Mhm.
And then when I distribute the phi or phi or whatever the heck it is, you get phi ac plus phi bd. Are they the same? Yeah. So because the answers are equal, the beginning is also equal, and the proof is done. And you can do that for every single one. It gets kind of tedious, especially for a couple of here. This one's easy to prove. Now, what are properties for? Well, they're to make your life easier if you're dealing with a problem and you have this. This one's kind of messy to calculate. This one's actually easier to add two vectors together and then do a dot product. And this one comes in really handy, the v dot v with the magnitude squared. That's probably the most important out of all of them, is this one right here. And we'll be using that later on. All right. Next little topic, and probably a quite important one. Oops, can't spell today. To find the angle between two vectors of force or whatever. To find the angle between them. This is going to get messy. So I probably should move it over there. Now, I'll do the setup here and then I'll draw my picture over there. So the setup. B and W. B and W are two non-zero vectors. In other words, neither of them is 0, 0, or 0i, 0j. So they have something to them. So the first thing you do is you let vector v equal a1 sub. I'll write it in ij notation. Not super necessary, but I'll write it both ways. A1, B1. A1, B1. Let V, or W, I'm sorry, equal A2I plus B2J, or just plain old A2, B2. A2, B2. Okay. Then I get to ask a question. If U is equal to B minus W, I read that right? Yep, B minus W. What's U equal?
Zero.
No. If V is this, A1, B1, and W is A2, B2, then what's U if it's V minus W?
A2 minus B1, B2.
A2 minus A1?
A1 minus A2.
A1 minus A2, comma?
B1 minus B2.
All right. This is going to be a little hard in our picture. All right, so the picture of all of this. This is the part you're not going to like. So if you don't want to write anything and you just want to pay attention to what's going on, the end result is the formula. But I like showing where formulas come from, so I put you through a little torture. Here's the picture. Coordinates, draw the picture. There we go. Coordinate system. Two vectors. One of them being V, one of them being W, whatever the heck A, B, A1, B1, A2, B2 are. The coordinates are at the end of those arrows. Then I'm going to draw one more vector. How do I draw V minus W? Do you remember? It was that last one I came up with.
You started it. W and go to that one.
V minus W.
Or you started V and go that one.
You go backwards of what you're thinking. So V minus W would be here. Oh, I did it backwards, didn't I? I think I even drew it in my notes. No, I have it right. Backwards is up. This is the arrow over here. This is the dot
So
over
I was right to touch
here. Yeah, it starts at W, it goes back to V. V minus W. If you had a negative W, it would be coming down here. If you drew your parallelogram, your vector would be going in that direction. Okay, so there's our pretty setup. Now the interesting part is I'm looking for this angle, theta. That's my goal, is to find that theta. So what do I have? What kind of picture? I can find that, if I know what V and W are numerically, I can find the magnitude of V, I can find the magnitude of W, and I can find the magnitude of V minus W, right? So I can convert these all into magnitudes. What does that tell me about this picture? I have a number on each one of these sides.
Kind of triangle.
Any kind of triangle. I have 3 sides.
Size, an angle.
Side, side, side.
I have a side, side, side. So what formula can I use?
Sides.
I know.
Cosines.
Law of cosines. So if I have all the sides, I can use law of cosines. All right, so the law of cosines, I'll write out the formal formula. You know, where C is the side opposite the angle you're looking for. Well, the side opposite of the angle I'm looking for has a magnitude of V minus W. So over here I'm going to put the magnitude of V minus W squared. So length of that side squared is equal to, well, A and B are just V and W, so magnitude of V squared plus magnitude of W squared minus 2 times the magnitude of V, magnitude of W, cosine of the angle I'm looking for. So far, just law of cosines. Problem. Well, yeah, it gets kind of messy after this. Remember, V minus W is A minus A and B minus B as its components. And if I want to find the magnitude of it and square it, the square just gets rid of the square root, then I have to square the first one, square the second one, and add them together. Okay? So this becomes A1 minus A2 squared plus B1 minus B2 squared. All right?
Wait, why did it change to the plus? Oh,
Distance formula has a plus in between them.
but I thought it was V minus W.
The magnitude, the vector of V minus W is this: A1 minus A2, B1 minus B2. To find the magnitude, you take both of them and you just square it and add them together and square root it. But the square on the thing takes away the square root. You want me to write the square root in there just in case? Okay.
Sorry.
All right, same thing for magnitude of V. This is just going to be A squared plus B squared. The magnitude of, A sub 1 squared, B sub 1 squared. And the magnitude of W is going to be A sub 2 and B sub 2. So A sub 2 squared plus B sub 2 squared. Now, I'm going to leave the rest of it. There's a reason. We don't need to look at the rest of it right now. We have enough A's and B's on the board to take care of things. All right, take the next step. What do you think I should do? Well, there's nothing to combine on the right-hand side. But what can I do on the left-hand side?
Solve.
Solve?
Factor.
Both.
Not factor. Factor means break it into parentheses.
That thing you do. I don't know what to call it, but
Foil?
yeah.
Foil it. Expand is another way of phrasing it. So what's A1 minus A2 all squared?
A1 squared.
A1 squared
minus 2a.
1A2. And then plus A2 squared.
Alright. I'll write underneath it the b1s and the b2s. They're exactly the same. It'll be b1 squared minus 2b1 b2 plus b2 squared equals, well, all of this. So I'll just ditto. I don't want to write it all over again. Now, if you look on the left-hand side, there's an a1 squared and a b1 squared. If you look on the right-hand side, there's a a1 squared and a b1 squared. What happens to them?
Cancel.
They cancel rather nicely. So, where's my a1? a1 squared, b1 squared, a1 squared, b1 squared. What about the a2 squared and the b2 squared?
Cancel.
They cancel rather nicely too, so they're gone. And then what's left over is the fun part. So this is negative 2a1 a2 minus 2b1 b2 is equal to negative 2 magnitude of v, magnitude of w, cosine of the angle we're looking for. Whew. How many terms are left?
3. Oh,
Both sides, all three, right? What do they all have in common?
2.
A negative 2, get rid of it. So then you get a1, a2 plus b1, b2 is equal to magnitude of v, magnitude of w times magnitude of w, cosine of theta. Almost there. The hard part's over. Now recognition is the rest of it. Remember identities, you had to recognize things? What the heck is a1, a2 plus b1, b2? Now go back to your original vectors. a1, b1 is vector v. a2, b2 is vector w. So what the heck is a1 times a2 plus b1 plus b2?
v dot w.
V dot w. So over here you get v dot w is equal to the magnitude of v times the magnitude of w cosine of theta. This is actually another definition of how to take a dot product. How many are you going to take a dot product that way? Nobody. Why? Because it's really, really messy. But it does define the dot product as the magnitudes times this cosine of the angle that separates them. So it has some relevance to it. But it also allows us to find out what theta is equal to. So, example. For example, let's do it in red. For example, find the angle between these two vectors. Let's draw approximations of them just to see if our answer comes up relatively right. Where's negative 3, 7? What quadrant? Second quadrant, so 3, 7 is something like this. So that would be V. Where's negative 2, negative 5? Negative 2, negative 5, probably right about there. And what we're looking for is the angle between these two vectors. Do you think it's less than 90 degrees or bigger than 90 degrees?
Bigger.
It's bigger, and definitely less than 180. It's always going to be less than 180. All right, so what do I need to do? Well, the formula says I need a few things. I need v dot w. I need the magnitude of v, and I need the magnitude of w. So some side work, v dot w. What's it equal?
W dot v.
Well, v dot w, yeah. And what's it equal?
Positive 6
Nope. Well, positive 6. Okay, I'll go with that. Plus
negative 35.
a negative 35, better known as
You know what
Negative 29.
negative 29. Give me that calculator. All right, we also need to know the magnitude of v. Well, how do you find the magnitude of v? Well, it's the square root of the components squared added together. So, negative 3 squared
Yeah.
It's the components squared added together. So negative 3 squared is 9, plus 7 squared is 49. So the magnitude of V is
Oh, 58.
seriously. Oh, yeah. If it's a 9, it's 1 less. 58. Does it break down?
Well, 7, I don't know.
2 goes into 58 how many times?
29.
I'm taking your calculators away from you. 29, and 29 is prime. Magnitude of W, which would be the square root of. Doesn't count.
Square root of 2 and 25
Oh,
plus 27.
4 and 25. Square it.
You just 2.
Okay, hang on. It's 29.
Yay! You didn't even need your calculator for that. That's awesome. All right, and then you just plug it into the formula. I mean, you can think of it that way. So the first thing is V dot W is equal to the magnitude of V, magnitude of W, cosine of theta. So V dot W gets replaced with
B, 20, what is it? 29.
negative 29. Magnitude of V is the square root of 58. Magnitude of W is the square root of 29 cosine of theta. Right. How do you solve for theta?
Move it to the other side.
Move the numbers to the other side, the 58 and the 29. So divide them across, and you get cosine of theta is equal to negative 29 divided by. Do you like the notation with 2 square roots or just 1?
No.
Can I just multiply the numbers and leave them under the square root, or is that legal? Or this time it is. So it becomes the square root of 58 times 29. Don't multiply those two together, it's not worth your effort. But your calculator you might want to, but everybody else has the other calculator, so you'll have to put a little more writing down. And then over here, of course, would be the answer. Okay, how do I get cosine away?
In cosine.
Cosine inverse. So the measure of angle theta is going to equal cosine inverse of negative 29 divided by the square root of 58 times 29. The reason I wanted to get the two numbers under the square root is because if you leave them separate and you type it in your calculator, you're probably going to get it wrong because you forget the order of operations, or you forget to put a parentheses in the front and the parentheses in the back. But if you put it under the square root, it automatically does both parentheses. So what's the measure of angle theta approximately?
Hold on.
Oh, you still have paperwork to do. Cosine inverse of negative 29 divided by the square root of 58 times 29.
35.
That came out actually quite perfect. That's actually kind of interesting. This is exactly 135 degrees. So that makes me wonder.
It's probably not right.
No. 58 is 2 times 29, right? So this you could pull out a 29. The 29s would cancel. You get negative 1 over the square root of 2, which is the same thing as square root of 2 over 2. The reference angle here is 45.
Oh my gosh.
Isn't that awesome? I gotta take a picture of this problem. I've never had one come up perfect.
Did you just make that up?
Yeah, I just made it up. Oh, I don't have to do that.
Oh my goodness, it's a miracle.
That's awesome. That it came out perfect.
Guarantee we're gonna get this in our emails later tonight.
Not that. But I mean, usually when I make up problems, they come up quite messy, and that one,
Wait, don't erase.
I can't
Oh,
erase.
yeah, you
I can't erase this.
probably put it on Facebook.
Facebook. Yeah, look what I did. Didn't even plan it. Just randomly pick numbers. That's usually what I do.
Look at that and say, what?
Who cares?
Yeah.
I saw a picture. My wife actually sent it to me. It's a tree that